Hi, I'm Armita Tehranchi, and today I'll be sharing my final project on developing a code that uses deep learning to automatically generate descriptions for images. This is the table of content. I'm going to start with an introduction, a brief overview of my project, the architecture that I use, the results that I gained, and finally the discussion for future works. So I'm going to start with a brief introduction to explain what is image captioning. For example, this is a Coco Captions dataset, and the right upper pictures has a caption which is written "a large bus sitting next to a very tall building." So I'm going to use another dataset for my project. This is fully correct call. For example, we have this picture, a girl in a pink shirt, and it has 5 captions. For example, a child in a pink dress is climbing up a set of stairs in an entryway, or 4 more captions. Our model is trained on this dataset consisting of 8,000 images and over 40 captions. Each image has 5 captions, and we pre-process this data by tokenizing and embedding the caption to prepare for efficient learning. And you can see in here that we have a function which shows the picture with its caption. This project leverages a combination of convolutional neural networks, or CNN, for image analysis and long short-term memory, or LSTM, networks for generating descriptive text using the dataset that I mentioned. Now we use a pre-trained ResNet 18 model as our CNN encoder. This model is responsible for extracting detailed features from the input images and then passing them to LSTM units, which are specifically designed to handle sequence prediction problems. This combination allows us to maintain context and generate meaningful sentences. Observed from a lot of results that ResNet can encode better image features. ResNet architecture is a 100 to 200 layer deep CNN. To account for the problem of vanishing gradients, ResNet has the following scheme of skip connections. You can see it in here. These connections help in training deeper networks by allowing gradients to flow through the network without substantial loss. This for puzzle-based problem solving. Based on the sentence before, we can infer what the subsequent phrase will be, as you can see in here, based on the sentence before. By solving the drawbacks of our RNN with short time period memory, it has proven to be more effective than conventional RNNs. While processing inputs, LSTM may perform the necessary statistics. Via an overload gate, it may also discard the unnecessary statistics. Each LSTM unit uses gates to control the flow of information, deciding what to retain and what to discard, thus ensuring that the model generates relevant and context-aware captions. Our goal is to maximize the probability of generating a correct caption given an image. The section outlines a mathematical framework used in our image captioning system, focusing on the encoder-decoder architecture involving a CNN and an LSTM. So our objective function is the optimal set of parameters theta that maximizes the log probability of the correct caption S given image I. Then we have a feature extraction by CNN. The encoder part of our model uses a CNN to transform the input image I into a dense feature vector F, which I explain it in here. Then we represent a caption generation by LSTM. The decoder and LSTM generates the caption by predicting each word, which we define it as ST in here, in the sequence based on the feature F extracted by the CNN and all previous predicted words. So it started from S0 to ST-1. Each word, or ST, is conditioned on the image feature F and the sequence of previously generated words, with theta LSTM indicating the parameters of the LSTM. Then we want to optimize. The parameter theta encompassing both theta CNN and theta LSTM, and it optimized them using Adam Optimizer. This optimization seeks to improve the alignment between the generated caption and the ground truth captions in the training data, enhancing both the accuracy and relevance of the output captions. To apply the chain rule to the model, the joint probability over S0 to Sn is considered, where n is the length of the particular caption. Now I'm going to summarize the algorithm that I used. The model depicted in the algorithm utilizes a combination of CNN and LSTM networks to generate captions for images. At first, the CNN processes the input image to extract a feature vector that captures essential visual information. This feature vector serves as the initial input for the LSTM, which is designed to generate text sequentially. As the LSTM outputs prediction for each word in the caption, the highest probability word is selected at each step, and its embedding is fed back into the LSTM as the next input, as we shown in the previous slides. This loop continues until the model predicts an end of sentence EOS token or reaches a predefined maximum length. The model is dynamic, incorporating feedback from each step into the next, enabling it to construct contextually relevant and coherent captions based on the visual content provided by the CNN. Final result. In the left figure, I didn't use any dropout layers, and also my architecture was simpler, so I faced an overfitting problem. Because of that, I changed my algorithm to a more complex model, resulting into nearly same train and validation loss, as you can see in the right picture. Then I was checking the difference between frozen and unfrozen model. In frozen model, we freeze all the layer of ResNet except the last layer. Let's see the result of that. The left picture shows the unfrozen model, while the right figure shows the frozen model. What is freezing layers? Freezing layers provides stability and prevents overfitting by relying on general features learned from extensive pre-training. In contrast, unfreezing layers allows the model to adapt more deeply to the specific characteristics of the captioning task, but at the risk of overfitting. To generalize it, the frozen model maintains better generalization as seen in less volatile validation losses. In contrast, the unfrozen model, while potentially more powerful, requires careful handling of epochs and regularization to harness its full potential without overfitting. A capability to generate more contextually rich captions as indicated by higher blue score on some complex scenes. I'm going to talk about blue scores in the next slide. However, in this case, both models yield nearly identical results, but the frozen model benefits from faster training speeds. So if we have a model that we care about the time constraints, we are going to use the frozen model. But if the accuracy and the blue score is important for us, we can sacrifice the time, we can use unfrozen model. I only used 20 epochs as I had limitation of using GPU on Google Cloud. It's obvious that the initial model without dropout layers has the highest validation loss, while unfrozen model has the lowest, but it is not that much different from frozen model, which is not that much time consuming. For example, let's see. At first, when I have the initial model, the validation loss was 5.27, but the frozen model had 20.77. And the unfrozen model had 20.66. So I changed completely the initial frozen model because it wasn't giving me a good result. And then we can see in the 20 epochs, this is 26 for the loss for frozen model is equal to loss for the unfrozen model, and the validation loss is decreasing just a little bit, so it doesn't worth it to sacrifice the time between these two models. So this is the final result for 3 different models that I had. The blue score of unfrozen model had the highest percentage, Blue score is between 0 to 1, and 1 shows the human capability of understanding the image, which is the highest score. For example, in here, the blue score is 0.7, nearly 0.7 for the unfrozen model, and for this one is 0. And this is the initial model. I didn't calculate blue score for it because as I said, it was a bad model. For example, it says a woman in red shirt and black shirt standing on a bench, a large white and white and white and white dye, which shows it has a bias on color because of the overfitting that it had. In comparison with that, other unfrozen model had the score of 0, which shows that it wasn't that much different from frozen model. So if we care about time a lot, we can use the frozen model. To summarize, we had an image captioning system using a CNN RNN architecture, and we trained it on the Flickr 8K dataset. For future, we can use CLIP model. In CLIP, we can see a significant step forward, and then we have the epochs. We can increase it because I had the limitation of GPU. So by increasing the epochs, we can refine the understanding of complex in image features, and then we can have the dataset expanding. Again, because of the limitation that I had, I use the Flickr 8K, but we can use MS Coco or conceptual captions, which can enhance the model's robustness and generalizability. These are the references that I have used, and thanks a lot for listening to me. And this is my email. You can reach out to me if you had any question. Thank you.